Okay, so today we are going to look at some problems from chapter 21, where we discuss radioactivity, some nuclear chemistry. A pretty interesting chapter. Links closely back to chapter 15, where we talked about the chemical kinetics. Right, so that might be something that you want to take some time to review, before you get into the calculations part of this chapter. We're going to start off by looking at some decay problems, though. And before we start here, I wanted to just do like a little summary of the different types of decay processes that we have to make sure that we're all on the same page here. When you're looking at different types of chemical decay, you're going to be seeing these processes represented as looks like chemical equations almost. All right, but in these chemical equations, you're going to see your isotope notation come back up, right? So if you remember, I mean, this was all the way from like chapter 2. When we have isotope notation, that's something that looks like this. We have A, Z, X, okay? And each of these symbols represents something specific. So this X value is going to represent the actual chemical symbol of the element that you're looking at. You can find that chemical symbol on the periodic table. The Z value is going to be the atomic number. Okay, and you're going to notice that these two values, they are going to match up because the atomic number tells you what the chemical symbol is, and the chemical symbol tells you what the atomic number is, right? And the atomic number also represents the number of protons. All right, and then this value up here, this A value, this is going to be the mass number. And the mass number represents the number of protons plus the number of neutrons. Okay, so when you see kind of these nuclear equations written out, you're going to see different isotopes kind of undergoing the radioactive processes. Right, so we can look at an example of one type of radioactive decay just as like an intro here. So we'll look at the decay of uranium-238. It's going to decay via alpha decay. And we'll talk about the different types of decay in a minute. Now, when they give you this notation here, uranium-238, they're telling you all of this information, okay? You can find uranium on the periodic table. When you find uranium, you're going to know its X notation, and you're going to know its atomic number, all right? So you know that uranium is going to be U, and it's going to have 92 protons. So that's going to go as your little subscript down here on the left side. You also know that the mass number is going to be 238, and that mass number goes up top. All right, now we know that the uranium is going to undergo alpha decay. And when an isotope undergoes alpha decay, that means it's going to emit an alpha particle, and an alpha particle looks like this. 4 on the top, 2 on the bottom, and then helium. All right, and what you're going to notice is that the other nuclide that forms is going to be whatever's left of this isotope after we remove these particles. Okay, so we had a mass number of 238. Well, our mass number is going to be 4 less now. So our new mass number is going to be 234. We had an atomic number of 92. our new atomic number rather, is going to be 2 less. So it's going to be 90. So now I'm going to look up on the periodic table. I'm going to see what element is atomic number 90. And that's going to be thorium. So I'm going to write that down. So that's going to be the process of uranium undergoing alpha decay. Okay, now what I want you to notice here is that your superscript on the left is going to be the same as your superscripts on the right added together. That's always going to be true in any nuclear reaction you're looking at. And the same is true for your subscripts. If you take the subscript of the reactant and add it to the subscripts of the products, you're going to get the same value. Okay. Also notice that when this Z value changes, the element identity changes. Because when you change the number of protons, it changes the identity of the element. Okay. For vocabulary purposes, this isotope is going to be called the parent nuclide. And this isotope is going to be called the daughter nuclide. And this represents the type of decay. Okay. So let's talk about the different types of decay. So we already started talking about alpha decay, so we might as well start there. So when we have alpha decay, which you're going to see represented, this little alpha term gets represented like something like that. Okay, that's when your nucleus is going to emit an alpha particle. Which you're going to see, it looks like a helium-4 nucleus. That's why it has that helium notation in it. Okay, so the alpha particle itself looks like this. Okay, and this is going to be a helium-4 nucleus. All right, so that's going to be alpha decay. And we saw that happen before. Our uranium-238 emitted an alpha particle, and then the uranium-230 or uranium-238, I don't remember, I don't know if I messed up that number. So the uranium-238 emitted an alpha particle, and then what was left after the alpha particle was emitted was that thorium isotope. Next type of decay is called beta decay. Okay, and that's going to be represented by like, it looks like a fancy script B. Okay, and beta decay is when you have an unstable nucleus and it ends up emitting an electron. All right, and you might be thinking, well, that doesn't make sense because there are no electrons in a nucleus. But what happens when you have an unstable nucleus is that a neutron can actually change into a proton. And when it does that, it ends up emitting an electron. Okay, that's how beta decay is going to work. I mean, I'm going to write has a neutron that changes, but it could be more than one if multiple processes happen. emits. And I'll write the process out for you too, so you can see what it looks like. The beta particle, like you see how this was the alpha particle, so the beta particle has its own notation also. The beta particle is going to be 0, where your mass number would go. -1 down here where your protons would go, because it's kind of representing an electron. An electron's like your opposite. And then we have the little e. Okay, so this is going to represent an electron that's going to be emitted. And the process of beta decay looks like this. So we have an unstable neutron. This is the representation of a neutron, right? Because it's not going to have any kind of charge, so it has no proton. And it's got a mass of 1. So that neutron is going to convert into a proton. This is how we'd represent a proton. And 1 electron. And notice, just like we saw before, just write this down. Just like we saw before, the superscript on the left, when I add up the superscripts on the right, they add up to the same number. When I have my subscript on the left and I add up the subscripts on the right, they add up to the same value. Okay, so that's still true here. All right, that's alpha and beta. The next one is going to be gamma ray emission. Remember, your gamma radiation is going to be that really high energy radiation. And your gamma ray is going to look like, it's like a weird little symbol like that, something like that. Your gamma rays have no charge, they have no mass. So that's different than the alpha decay and the beta decay that we saw. Okay, your gamma rays are just going to be high energy photons. Okay, so you're not going to see a change in your mass number or in your atomic number when you have gamma radiation as part of your nuclear decay process. Okay, and when you are going to note that you have gamma radiation, the kind of particle notation that you would use would be 0, 0, right? Because it's going to have no mass or charge. And then that little weird thing. That's what I call it. Some kind of like fancy Greek letter that I don't know the name of. But that'll be your gamma radiation. Okay. Next type of radiation is going to be positron emission. And positron emission is going to happen when you have an unstable nucleus that emits a positron. And we'll look at what a positron is in a minute. Your positron particle is going to look like this. Your positron particle is called the antiparticle of the electron. Okay, it's going to have the same mass as an electron, but the exact opposite charge. Okay, so when you have positron emission, you're going to have a proton that's going to be converted into a neutron, and it's also going to emit a positron. Okay, so we're going to have, this is the process that happens. We have a proton, and it's going to convert into a neutron. And remember that when we add the right and left sides of these nuclear equations together, numerically they have to balance out. So what we're going to be left with on this reactant side is a superscript of 0 and a subscript of +1, which represents our positron particle. Okay. So a proton converts into a neutron. And this becomes important later when we're looking at types of decay that are likely to happen. Knowing these processes is important to understanding what's happening in those situations. Okay. And there's one more type of decay that we need to look at, and it's called electron capture. Let's see if I can fit it all down here. This is when you're going to have a nucleus that ends up pulling an electron from its inner orbital into itself. Okay. And when it does that, it's going to convert into a neutron. Okay, and I'll show you the process. Okay, so you're going to see that you have a proton, and you're going to capture an electron. So you're going to have the electron on the reactant side this time. And what's going to be left? Well, when I add 1 plus 0, I'm going to have 1. When I add 1 plus -1, I'm going to have 0. And this indicates a neutron. Okay, so you end up having your atomic number decrease by 1 because it ends up losing one of its protons. Okay, so the identity of the element then is going to change. All right, so those are the different types of nuclear decay. Now, because we've looked at all the different types of nuclear decay, we can actually look at these next few problems, and we'll have a better idea of what to do with them. So that first question that we put up asked us to write the nuclear equation for the alpha decay of two isotopes, radon 224 and polonium 216. Okay, so remember, alpha decay just means that we're going to be removing an alpha particle from our initial isotope and then figuring out what remains. Okay, so starting here with our radon 224. Right. It's not radon, it's radium. So here we're going to have an alpha particle. Okay, I like to write the type of decay first because it like helps me keep track numerically of what's going to be happening with my other particle. So if we take the radium 224 and we rewrite it in isotope notation, we're going to end up with Ra. We'll have a 224 up top. And if you look up radium on the periodic table, you see it's atomic number 88. And that's right on the periodic table. Okay, let's make the 8 clearer. Now, what's going to be left over here? Well, 224 minus 4, it's going to be 220. 88 minus 2 is going to be 86. And I'm going to look up element 86 on the periodic table. That's going to be radon. So this is going to be my nuclear equation for the alpha decay. All right, for my next example, I've got polonium 216. Okay, so I can rewrite this. I'll look up polonium on the periodic table. It's atomic number 84. I know it's going to undergo alpha decay, so I need to put my alpha particle there. 216 minus 4 is going to be 212. 84 minus 2 is going to be 82. If I look to see what element number 82 is on the periodic table, I see that it's lead. So there is my nuclear equation for this alpha decay. All right. The next, we have a few examples in this next one of all the different types. So if you want to take a minute to write some of this down. But we're going to write a nuclear equation for each type of decay here. You get to see some weird elements too in this part of the textbook, which I like, because we never really talk about the radioactive elements. But for part A, we're starting with some beta decay in berkelium 249. Okay, and then we'll do positron emission. In oxygen 15. And then electron capture in iodine 111. All right. So first, our beta decay. We'll look up the berkelium on the periodic table. It's atomic number 97, so we can write out our isotope notation here. Okay, and we know that it's going to be losing a beta particle, which is going to be 0 and -1. Okay, so my superscript up here is going to be easy because 249, 0 means that this is going to be 249 still. All right. Now I have to ask myself, what plus -1 equals 97? Okay, well, the answer to that is going to be 98 plus -1 equals 97. So this is going to have to be my subscript for my new isotope. Okay, because I have to be able to add the subscripts on the product side together to get the subscript on the reactant side. Now I have to look up and see what element number 98 is. It's californium. And that is going to be the equation for my beta decay. All right. The second example is the positron emission for the oxygen 15. So again, I'm going to start by writing out my isotope notation for oxygen 15. Okay, and I'm going to put a positron as my first product. And the positron is going to have a 0 on the top and a +1 as the subscript, right? Because again, it's going to be the antiparticle for the electron. Okay, so again, I see that I'm going to get 15 back out as my other superscript because 15 plus 0 is 15. And now I need to figure out what my subscript is. Well, 7 plus 1 equals 8. So 7 is going to be my new subscript. What element has an atomic number of 7? That's going to be nitrogen. All right. The third example here is going to be electron capture of iodine 111. Okay, so when you have electron capture, that means that your decay particle is going to be on the reactant side. Okay, not on the product side. So you have your iodine 111, which you're still going to write out the isotope notation for. Iodine is atomic number 53. And in this case, the iodine 111 is going to actually catch an electron. All right. And when it does this, right, what happens here? 53 plus -1. I'm going to end up losing a proton. So I have 52 protons on my product side. But my mass number is not going to change. So my new element is going to be the tellurium. And those are my 3 nuclear equations for the first part. Okay. The second part was, this one's interesting. I'll put it back up in case you missed it, because that's going to be a good one. This is to write 3 nuclear equations to represent the decay sequence that begins, we're starting with U-235. And then we're having an alpha decay, a beta decay, and then another alpha decay. Okay, we'll start there. So we're looking at this entire process. Okay, I love questions like this. I think that these nuclear or radiation questions are so fun. So we're starting with our uranium-235. Okay, so we write our first isotope notation, and we see that it's undergoing alpha decay. Okay, so we know that 235 minus 4 is going to be 231. 92 minus 2 is going to be 90. That's going to leave us with some thorium. Okay. Now our thorium is going to undergo beta decay, right? So we're going to, I'm going to put that back down here. 231, 90. and we're going to have 0, -1. All right, so 231 and 0, still going to be 231. I have a -1 over here and I have a 90 over here. That means that my subscript here is going to have to be 91, because 91 minus 1 is going to be 90. And that is going to be protoactinium. And then our protoactinium is going to undergo another alpha decay. So we're going to have our 23191 PA. Uh, 231 minus 4, 30, 27. 91 minus 2, 89. Look up number 89 on the periodic table. That's going to be actinium. And that is your 3 decay sequence, right? So this was your alpha decay, this is your beta decay, and then this is your next alpha decay. And this is your final isotope product. Okay, the next question asks us to write the nuclear equation for the positron emission of sodium-22. Okay, the positron emission. Of sodium-22. And again, you just want to start by writing out the isotope notation for sodium-22. So it's going to be a mass number of 22, an atomic number of 11, chemical symbol for sodium. Positron emission means that we're going to be emitting that positron particle. And that's going to be a 0 and a +1. Okay, so what's left after my positron particle is emitted? I'm going to have 22 for a mass number, and I'm going to have 10 for an atomic number, because 10 plus 1 is 11. Number 10 on the periodic table is going to be neon. All right, the third question in that set is going to be write the nuclear equation for the electron capture of Krypton 76. Okay, so again, I'm going to start by writing out the isotope notation for Krypton 76. Krypton is number 36 on the periodic table. Electron capture means that that decay is going to be happening, the decay particle is going to be on the reactant side. So I'm actually, the krypton is catching the electron. And what's going to be left after it does that? I'm going to still have a mass number of 76, but I'm going to have an atomic number of 35. Okay, and atomic number 35 is bromine. Okay, the final question is also another interesting one. Let me put it back up. Because it's just asking us, it's like, it's still a decay question, but it's a different type. This one says that you have potassium-40 and it can decay to produce argon-40. What kind of nuclear decay is happening, basically? We can use those two isotope notations to figure out the type of isotope decay. Okay, so let me just write out, you have potassium-40 and it's going to argon-40. And for a question like this, I would suggest writing out the two isotope symbols and then using the isotope symbols to figure out the type of electron decay that's happening. Okay, so we have 40 on top, 19, and we have 40 on top and 18. Okay, so we know that the type of decay that's going to be happening here is going to be a particle that has a 0 as its superscript. Okay, and there are two types of decay that should kind of jump out at you here. All right, there's only one type of decay that's going to have a 0 on top, and that's going to change the subscript. Okay, and that's going to either be electron capture or your positron emission. Okay, and either one can be valid here, because if you have electron capture, you're going to be adding an electron to your reactant side. If you have positron emission, you're going to be emitting a positron particle over here. So let's write out the equations showing both of these. Okay. So for your electron capture, you'd have 40, 19 potassium, and it's going to be grabbing an electron, and that's going to leave you with your argon 40 isotope. If you have positron emission, we're going to start with your potassium isotope, and you're going to emit a positron particle. And then what's going to be left is an argon 40 isotope, right? Because 18 plus 1 is 19, just like 19 minus 1 is 18. So either of these are correct in this case. Okay, both of those are valid decay methods for the type of decay that's being described here. All right, the next question is going to be asking us to kind of look at that belt of stability that's discussed in your textbook and to figure out what type of decay is likely to occur based on the isotope that you're looking at. Okay, so I mean, when you're looking at this belt of stability here, what you're really focusing on is the N to Z ratio here. Okay, the neutron to proton ratio. Let's take a minute to just review some of this stuff. Again, to make sure that we're all on the same page before we start looking at these problems. So the type of decay is going to depend on your N over Z ratio. And you see in like in your atomic numbers that are lower, that N over Z ratio is very close to 1, but that ratio gets higher and higher as your atomic number increases. Okay, and for the questions that we're going to answer, we're going to look at the chart to help us figure out what the relationship between the neutrons and the protons are for each of the isotopes. Okay, in this N to Z ratio, the N stands for your neutrons, the Z stands for your atomic number, and your atomic number indicates the number of protons you have. Okay, so if you have an N to Z ratio that's too high, I mean, what does that mean? It means that you have too many neutrons. So if you're trying to think of the type of decay that would occur, it would be a type of decay that would convert a neutron into something else like a proton. All right. And the type of decay that does that is beta decay. Okay, remember the process for beta decay. That's when we take a neutron and we convert it into a proton and an electron. So when beta decay occurs, it's going to make our neutron value smaller. And it makes our Z value, our proton value, larger. Okay, so that's if our N to Z ratio is too high. If our N to Z ratio is too low, we have the opposite problem. Okay, we have too many protons, right? Our Z value is too big. We have too many protons. How can we fix this problem? We're going to have to figure out how to convert our protons into neutrons. They can do this via positron emission or electron capture. Okay, and like in the problems that we are about to look at, they're telling us to focus on the positron emission. Okay, and remember that for these processes, when you have your positron emission, for example, always go back to the process to look at this. That's when you have a proton. I don't know why I wrote that as a fraction. 1p. And it's going to convert, I did it again. It's going to convert into a neutron, and it's going to release that positron particle. For your electron capture, we're starting with the proton, and it's going to capture an electron, and you're going to be left with an additional neutron. So in both of these cases, your proton values are going to get lower, and you have neutrons on the product side rather, so your neutron values are going to get higher. So that's going to fix an N to Z ratio that's too low. All right, so hopefully that makes sense. So we're going to look at, we have 6 examples overall. And we're going to look at the isotopes, and we're going to figure out whether they're decaying via beta decay or positron emission. Okay, so our first set is going to be Mg228, Mg22, and MO102. Okay, and to figure this out, we're going to look at the atomic number for each of the elements. That's going to be our Z value, and we're going to put our neutron value over our Z value. Okay, remember that this number that they give us here, this is our mass number, and that's going to be our protons plus our neutrons. Okay, so for Mg28, we look on the periodic table and we see that we have 12 protons. because Mg has a Z value of 12. So the neutron value is going to be 28 minus 12. Right? Because our mass number is 28 and our mass number is protons plus neutrons. So now if we look at our N over Z ratio, we see that it's 16 over 12. You can divide that out, you get like 1.3. Now you can look back to the table that we have, or the chart that we have. I'll put up the chart again. And what you want to find is you want to find the place that would represent magnesium as close as possible on this table. And the atomic number for magnesium is 12. So we'll say that it's around here. Okay. Now, magnesium is still in the area where an N to Z, a stable N to Z ratio is about 1. So I'm going to just write that down on the whiteboard here. A stable N to Z for magnesium is about 1. So what we see here with an N to Z ratio of 1.3 is that our N to Z ratio is too high when we have magnesium 28. Right? This is too high. It's higher than our stable number, which is 1. If your N to Z ratio is too high, that means that magnesium 28 is going to undergo beta decay to stabilize. Because beta decay is going to decrease our neutron value and increase our proton value. And that'll get it closer to this value of 1. For our next example, magnesium 22, we're still using magnesium, so that's nice. We can keep that same stability comparison right down here. Okay. But now we're looking at magnesium 22. So our protons are still going to be 12, but our neutron value is going to be 22 minus 12. Okay, so our N over Z value here is going to be 10 over 12, which is going to be around 0.83. And 0.83 is too low. When the N to Z ratio is too low, positron emission is going to occur. Okay, that's what's going to occur to stabilize. All right, so these ones were nice because they were both, they were both magnesium, so that was easy. Now we're going to look at a different element and see how we figure out what the stable region for molybdenum is, because molybdenum is bigger than magnesium. Okay, so to do that, we're going to have to look back at our table, at our graph. MO102. If we look up molybdenum on the periodic table, we see that it has a proton value of 42. Okay. Now, on the table, we can use that proton value to figure out. I'll share the screen again. Right, we can use this proton value to figure out where our stability is. Okay, so I'd say that this little green, this green section here, this is our actual, these are our stable nuclei. Okay, so the N over Z is only 1 for the smaller elements. Once the elements get larger and once they have more protons in them, the belt of stability deviates from that N over Z value of 1. So we need to refer back to it and say, well, what's our new stable N over Z value? And for an atomic number around 42, we're going to see that it's pretty close to this value here that they gave us. So we can say like 1.2, somewhere in the 1.2 region, right? Maybe 1.25 or something like that. That's our stable. So MO nuclei will be stable at an N over Z ratio of, I'll say 1.25, somewhere around there. I know it's not exact, but 1.25, 1.3 maybe. And we're just basing it on that stability line in the chart, okay? So with our isotope here, we're going to figure out our neutrons by taking 102 and subtracting our protons from it. So we have 60 neutrons. So our N over Z is going to be 60 over 42. And that's going to give us a value of around 1.43. 1.43 is higher than 1.25, which makes it too high. If that value is too high, then the molybdenum 102 is going to undergo beta decay to stabilize. Okay. All right, let's look at the next set of examples. We have 3 more of these that we can look at. Okay, so let's look back at these next 3. This is a good time to try to pause this and try these on your own. So I'd say a good place to start off with each of these is to use the chart and see where the ideal N to Z ratio is for something that's stable, okay? So you want to find each of these elements on the periodic table first so we could figure out what their atomic number is, right? So lead is going to have a Z value of 82. Xenon is going to have a Z value of 54. Now, if you look back to the chart, we can go back to the chart together. Okay. If my Z value is around an 82, and I trace it up here, I see that I'm going to have an N to Z ratio that's stable. Stable N over Z is going to be around 1.5 something. We see that one of the examples is mercury that has an atomic number of 80, so and that's 1.51. So maybe for lead it's going to be 1.52 or something like that. For our xenon, that has an atomic number of 54. So we're going to be somewhere over here. Okay, so if we want to calculate an N to Z stable ratio for something that doesn't have a number attached to it on our chart, we're going to look and see what N value corresponds to the area here on our chart where we have stability. So here, right around here, where we have an N value of 50 something, if we trace that back to our y-axis, we see that the n value here rather is going to be somewhere in the 70s, right? Like, I don't know, maybe 72. You know, we're kind of estimating. Okay, but that's all right. That's going to help us calculate that value. So if we go over here, based on our estimation, we should have a stable region for the xenon at around 1.33. Okay, so these are going to be our goals. So for PB192, we're going to get our neutron value by subtracting our mass number from our protons. 192 minus 82, that's going to be 110. For our lead, 212, we're going to still have that stable region of around 1.5 something. And our neutron here is going to be 212 minus 82. And our neutron value for the xenon, 114 minus 54. Okay, so now we can calculate these N to Z ratios. So this is going to be 110 over 82, 130 over 82, and 60 over 54. So this is going to be 1.34. This is going to be too low. Right, and then we have a value that's going to be too low. Then we're going to have some positron emission. Because the positron emission will help increase this value. So it gets closer to 1.5. For this value here, we have like 130 over 82, and that's going to be 1.59. 1.59 is too high for this one, right? We said it was around 1.5, like 50, 51, 52, something like that. But 1.59 is a lot closer to 1.6 and 1.5. So this is still going to be too high. So this is going to undergo some beta decay. Okay, and then for our xenon 114, 60 divided by 54 is going to be 1.11. 1.11 is going to be too low. And that means that our xenon 114 is going to have to do some positron emission to stabilize. All right, so that's how we're going to use that. Ooh, the next set of questions, let's pull those up here. We have to like flash back a little bit to our chapter 15 for this part. All right, I told you that that was coming. You know, the questions that you're looking at, like here, they're asking us about, they're talking to us about half-life. They're asking like how much time is going to take for this particular amount of material to decay. That all goes back to your chemical kinetics, right? Your rate laws. All right, so gotta like go back in time a little bit for that. One thing you want to keep in mind is that all of your radioactive decay, all of it, why can't I spell when I write these things? It's all going to decay via first order kinetics. So your first order rate law, your first order half-life, your first order integrated rate law, we need all of that to do these types of problems. Okay. So remember that your rate law for your first order reactions is rate equals K times the thing that you're looking at raised to the 1. In this chapter, instead of writing the concentration of A, they substitute this in with this value of N, which is going to be your radioactive nuclei. Okay, but you're still going to take this amount of radioactive nuclei and you raise it to the first power, which means that it's just K times N. Your half-life equation for your first order reaction is still going to just be 0.693 over K, and this is still going to be your rate constant. In both of these, this is K value is your rate constant. And then you're going to have your integrated rate law. And that's going to be the natural log of N sub T equals negative KT plus ln N sub 0. And what these notations are standing for, the little n with the little 0, that's going to be the initial number of radioactive nuclei. This N sub T value is going to be the number of radioactive nuclei after a certain amount of time passes. So I'll just write that at like after T passes. This is still going to be your rate constant. And then that's going to be your time. And note that whatever the units of your rate constant are and the units of your time value are, these have to be like the same time values. Okay, so if that involves a conversion or whatever, then make sure that you do the conversion so that the time units are the same here. All right. But we're asked this first question. It says a plutonium 236 is an alpha emitter with a half-life of 2.86 years. If a sample initially contains, so I equals 1.35 milligrams of Pu-236, what mass of Pu-236 is present after 5 years? So this, I guess we call this our N0, and we're going to look for NT. And our T value is going to be 5 years. Okay. So this starts to look a lot like those rate law problems from chapter 15. We see right away that because we have a concentration at an initial time and a concentration after some time has passed, that we are going to need to use the integrated rate law to solve for this. Okay. But before you can do that, you need to know what your K value is, right? Your rate constant. And we're going to be able to figure out what the rate constant is by using our half-life equation. Okay, so let's box this off, and then we're going to write a little note up here. And it's going to say find rate constant by using half-life. You're going to have to do this all the time in this chapter. Okay. So we know that T1/2 equals 0.693 over K. That means that we can find K by taking 0.693 and dividing it by our half-life. Excuse me. So that means that our K in this case is going to be 0.693 over, what was it, 2.86 years. And that's going to be 0.2423 inverse years. So years to the -1, right? Because years is on the bottom of this fraction here. So this is going to be our K value. Once we have that K value, now we can do the integrated rate law. And I wrote the integrated rate law for you. I wrote one version of it in my last writing on the whiteboard. I'm going to write it a little bit differently here because both types of equations are correct. In this version, I have ln of nt over n0 equals minus kt. It honestly just depends on what values you have as to what version of the integrated rate law you want to use. The one that I wrote on the previous whiteboard was this version of it, where you have ln of nt minus ln of n0 equals minus kt, and then we put the n sub 0 on the other side. But I think it might be easier to solve it with this version, okay? Because we can plug in a lot of these values straight away, right? We know what our n sub 0 value is, right? Our n sub 0 is going to be 1.35 milligrams. So I'm going to plug that in. So I still have an NT up here, but my n sub 0 is going to be 1.35 milligrams. My K value is going to be 0.2423 inverse years. And the time that I'm looking at is going to be 5 years. This is what I was talking about also when I said make sure that these time units match. If your time value was given in like days, you would have had to convert your K value in terms of inverse days instead of inverse years. Okay. So just watch out for that. So now I'm gonna solve for this part of it. And I get ln of nt over 1.35 milligrams equals negative 1.212. All right. And what I'm going to do at this point is I'm going to raise both sides to the e here, so I can get rid of this natural log on this side. All right. So I am going to write more of this equation over here. Switch to a black marker so we can differentiate this a little bit. So this value raised to the e is going to be nt over 1.35 milligrams equals 0.2977. Okay, so that's what happens here. When I raise both sides to the e, I can get rid of that natural log, and now I can just solve for nt. So I'm going to solve for nt by multiplying both sides by 1.35 milligrams. So nt is going to be 0.2977 times 1.35 milligrams. And it's going to be 0.402 milligrams. So that's going to be the amount that's left after the 5 years passes. Okay. Let's look at that second part of the example. In this case, we're using the same plutonium 236, so we're going to be able to keep the same K value for the next part of the question. This asks, though, let me go back to the problem so you can look at it. See here it says, how long will it take for 1.35 milligrams of the plutonium 236 sample to decay to 0.1 milligrams? So now we're going to be looking for a time instead of a final concentration value or a final number of radioactive nucleotide value. All right, so let's erase this and write in our new info. Okay, so we're still going to have our K value. I'm going to rewrite it up here. K equals 0.2423 inverse years. So now I'm going to get rid of this. We're able to use the same rate constant because we're using that same radioactive isotope. Our N sub 0 is going to be 1.35 milligrams. Our N sub T is going to be 0.100 milligrams. And we are looking for our time. All right. So we can write out our equation. Our N sub T is going to be 0.100. N sub 0 is going to be 1.35. This is going to be minus 2423 inverse years, and then we'll have T. Okay, so I'll figure out this term first. 0.1 divided by 1.35. I'm going to take the natural log of that. So that's going to be negative 2.6027 equals minus 0.2423. Now I'm going to divide both sides by the K value, by the negative K value. Okay, and I get 10.7 years is the time that it's going to take for that decay to occur. Okay. All right. This is going to be our next example. Okay, so we're going to look at some radiocarbon dating examples now, and these are just going to be more examples where we use that integrated rate law and the half-life formula to solve the problems here. So take a second to write this down. I'm going to write it down as well. And then I'll bring up the whiteboard again. Okay, so this is our info. One thing that we have to know before we solve this problem is that the half-life for the carbon-14 is 5715 years. Okay, and that's going to be from your textbook. You don't have to know a lot of half-lives, but knowing the half-life of the carbon-14 is a good idea because it's so commonly used in these questions. And we're told that that living organisms have a decay rate of 15.3 disintegrations a minute times grams degrees Celsius. And that the skull that they're looking at has 4, not degrees Celsius, per gram of carbon. And that the skull they're looking at has a decay rate of 4.50 disintegrations, right, per gram carbon. I meant to write a little multiply sign. I wrote degrees over here. Oh well. So this is going to be our initial rate. This decay rate here, this indicates living organisms. This decay rate here is going to be this ancient skull that they found. Okay, and we're supposed to look at these decay rates and figure out how old the skull actually is. So we can do that using the half-life of carbon-14 and our integrated rate law. Okay, because we have a way to relate the rate of disintegration after some time has passed to the original disintegration rate, as long as we know the rate constant. So that's what the half-life formula is going to help us with. So we know that T1 half equals 0.693 over K. So if we want to know what K is, we're going to take 0.693 and we're going to divide it by the half-life, 5,715 years. And that's going to give us a rate constant of 1.213 times 10 to the -4 inverse years. Okay, so this is going to be our K value for this question and the next one. All right. Now we're going to look at our integrated rate law. So we have the ln of the rate after some time has passed over the initial rate equals minus KT. And we're going to plug in the info that we know. So the rate after some time has passed is going to be 4.50. I'm not going to include the units, but you can include the units if you want to. When we divide, the units are going to cancel out anyway. Over the rate initial, which is 15.3. That's going to equal minus 1.213 times 10 to the -4 years inverse 1 times time. Okay, so let's do that. 4.5 divided by 15.3 ln. So we're going to have negative 1.224 . Okay, now we're going to divide both sides by K. And we get 1.01 times 10 to the 4 years. So this is going to be the age of the skull. How old is the skull? It's like, I guess, 10,000 years old, almost 11,000 years old. Okay. For the next question, we're going to look, it's very similar. Okay, the next question says that a researcher claims that an ancient scroll from Greek scholars came from 500 BC. Its carbon-14 decay rate is 89% of that found in living organisms. How old is a scroll, and could it be authentic? So in this case, I'm going to leave that there because we're still going to end up using this K value because it's still carbon-14 that we're looking at. But in this case, we have we were given the rates in a different way. Okay, so in this case, they're telling us that the carbon-14 disintegration rate of this ancient scroll is 89% of that found in living organisms. We can assume that in living organisms that the rate is going to be 100% of what you would find in living organisms. So we were just presented this information a little bit differently, but what we're going to see is that we can plug these percentages into our integrated rate law, just like we did in chapter 15 with our chemical kinetics. So in this case, we're going to take the ln of 89 over 100 equals minus kT. Okay, and we're going to see how old this skull is. If the skull is really from 500 BC, it should be like 2,600 years old. 2,600, 2,000, 2,500 and change. So not quite 26, but close. All right. 89 divided by 100 ln. And we get 961 years is the age of the skull. So we would say that in that case, it's not authentic because it's only from like, 1,050 years ago or something like that, 1,006 years ago, but it's not 2,000 years old, right? So not authentic here. Fake. I mean, honestly, it's still pretty old. 900 years is pretty old, but it's not as old as they wanted it to be. Okay, so for these next questions, we're gonna have to do a little deep thought first, okay, before we can jump in here. This one's telling us that we have a meteor and it contains 0.556 grams of lead-206 for every 1 gram of uranium-238. So we're assuming that when the meteor formed, there was no lead-206. So all of the lead-206 that exists now happened after the time of formation. Okay, and we know that uranium-238 has a half-life of a decay from 238 to lead-206 of 4.5 billion years. Okay, so all of this lead-206 that happened is happening after the meteor formation. Right, so let's take a look at how we would approach this. So what we're saying is that right now, we have a meteor that has a ratio, but we can use these numbers to represent the full mass of the meteor. It has 1 gram of uranium-238 and 0.556 grams of lead-206. Initially, all of this lead-206 used to be uranium-238. Okay, so the first thing we need to do is figure out how much uranium-238 there was initially. And we can do that based on this number here. Okay, we've seen from some of our nuclear reactions already that when we're going from one isotope to another, there's a 1-to-1 ratio mole-wise there. So if we have 0.556 grams of Pb2O6. First, we can convert that into moles using the mass of the isotope here. So there's going to be 206 grams in every 1 mole. And we know that for every 1 mole of the Pb2O6, there's going to be 1 mole of uranium-238. All right. Now we can convert this into grams because every 1 mole of uranium-238 is going to have a mass of 238 grams. So if we had 0.556 grams of Pb2O6, that's going to be equal to 0.642 grams of uranium-238 that we had before, but it's now converted into lead-206. Okay, so that means that the total initial amount of our uranium-238 is going to be 1 plus 0.642 grams. Okay. So now we have an initial amount of our uranium-238, and we have our current value of uranium-238. So if we find our rate constant, we're going to be able to figure out how much time has passed. Okay, well then if we figure out the time that's passed, that's going to be equivalent to the age of the meteor. So to figure out our K value, we're going to use our half-life association. So to find K, it's going to be 0.693 divided by the half-life, which in this case they told us is 4.5 billion years. So that's 4.5 times 10 to the 9 years. And we get a K value of 1.54 times 10 to the negative 10 inverse years. Okay, now we can use our integrated rate law and solve for time. So we'll have ln of the NT value over the NO value equals minus KT. Our NT value is going to be the current time, and NO is going to be the initial, right? Or so I guess NT in this case is going to be our current amount of uranium, and N initial is going to be our initial amount of uranium. So that's going to be 1 gram over 1.642 grams. We're going to divide both sides by negative K. We end up with a real big number, but that's fine. say, I guess it's 2 sig figs because of the half-life calculation there. So it'll be 3.2 times 10 to the positive 9 years. That's the time, and that's going to be the age of the meteor. Okay. All right, let's look at that next question, or the second part of that question, which is going to be very similar. And we're going to use the same K value for this one because we're still looking at that PB206 U238 ratio. Okay, so they're saying that our ratio is going to be 0.145 grams of PB206 to every 1 gram of uranium-238 again. And again, now we're going to have 1 gram of the uranium-238. And it's not that we have only 1 gram, it's just that the ratio of uranium-238 to lead-206 is this 1.45 grams of lead to 1 gram of uranium. And we can look at this ratio in its smallest form, okay? Or in relation to just 1 gram of uranium. So if a rock was actually 975 grams uranium-238, we would know exactly how much lead-206 it would contain using this ratio. So we're going to find the initial amount, and our K value is not going to change. It's still going to be 1.54 times 10 to the negative 10 inverse years. We got that from the half-life. So in this case, we have 0.145 grams of PB206. So we're going to turn that into moles. There's a 1-to-1 ratio between our PB and our uranium. And in every 1 mole of uranium-238, it's going to be 238 grams. So we're going to end up with 0.1675 grams of uranium-238 that eventually converted into lead-206. Okay, so our initial amount is going to be 1 plus 0.1675. Okay, so that's how much uranium-238 we had initially. And now we are going to use our integrated rate law. So ln of 1 gram, which is our uranium now, over our initial amount of uranium, 1.1675, equals minus KT, so minus 1.54 times 10 to the negative 10 T. And we'll divide both sides by negative K. Okay, we end up with 1.01 times 10 to the positive 9 years for our time value here. So that would be the age of the rock, about 1 billion years old. Okay. The next question is a little bit different. So I guess the last type of calculation that your textbook goes over. And this is mass defect and nuclear binding energy. Okay. So we're going to look at both of these. So this says to calculate the mass defect and the nuclear binding energy per nucleon in mega electron volts for C16, which is a radioactive isotope of carbon with this particular, you'll notice that the mass values when you're doing mass defect and nuclear binding have many decimal places. Do not round them. You need them all. Okay, because the numbers are so similar that if you start rounding them, then you're not going to end up getting the correct answers. All right, so we're going to calculate two things here. We're going to calculate the mass defect and then the nuclear binding energy. So my guess is that before we do this calculation, we probably should just make sure that we all know what these terms mean. So when we're talking about the term mass defect, we're talking about the difference in mass that you have when you look at the nucleus of an atom, okay, the mass of a nucleus, and we compare it to the mass of the different particles that make up the nucleus. All right, does that make sense? So in like a helium atom, okay, in the nucleus, there's going to be 2 protons, and there's going to be 2 neutrons. All right, in the nucleus, the mass of the nucleus when these things are all together, this mass value is different than if you just added the mass of 2 protons plus 2 neutrons. So the difference between those two mass values is the mass defect. So the difference in mass between the nucleus of an atom and the sum of the separate particles that make it up. Okay, so for example, we just used that the helium example. If you look at the mass of a nucleus for helium, the mass is going to be 4.00260. Okay, now I showed you what particles make up the nucleus of the helium. There's going to be 2 protons and there's going to be 2 neutrons. Every proton is going to have a mass of 1.00783. Every neutron is going to have a mass of 1.00866. So we would expect that when we add these 2 values together, it would be the same as this value. Okay, but when we add these 2 values together, we end up with 4.03298 AMU. Okay, so this difference in mass is the mass defect. All right. Now the nuclear binding energy has to do with the mass defect. All All right, and that's going to be the amount of energy it's going to take to break that nucleus into the nucleons that make it up. Nuclear. So we want to break apart a nucleus into its component nucleons. And nucleons are anything that's in the nucleus, so protons or neutrons. Okay, so it should make sense to you that there would be an energy cost involved if you took a nucleus and you tried to break it apart. So that's going to be the energy value that we'll be finding. One other piece of information that we'll need before we can look at these problems is this definition of the mega electron volt. Okay, because we're going to see energy in terms of joules or mega electron volts. We need to be aware that for every 1 mega electron volt, which is MeV, that's going to be equal to 1.602 times 10 to the negative 13 joules. Okay. And when you look at nuclear binding energy, you're going to see that, you know, they ask you what is the nuclear binding energy per nucleon, right? So that's going to be another thing to keep in mind. You have to literally count the nucleons that make up a particular atom that you're looking at. What other value? Oh, one more conversion. One more mega electron volt conversion is that for every 1 atomic mass unit, that's going to be equal to 931.5 mega electron volts. Both of these conversions are in your textbook. Okay, if you want to look around at that section. So you can report nuclear binding energy as a value in joules or as a value in mega electron volts. Okay, if you're asked to calculate the binding energy per nucleon, you're then going to have to take the mega electron volt value that you calculated and divide it by the number of nucleons in that atom. So if we were looking at helium, helium is 2 protons and 2 neutrons, so that's a total of 4 nucleons. So we would take our value and divide it by 4. Okay. All right, so I think we can look at this problem now, and we can take a look at how we solve it. Actually solving the problem out it's not that complicated. Okay, but it's just knowing everything else leading up to it that makes it a little more complicated. So here we're looking at we're calculating the nuclear mass defect and nuclear. You have to calculate the mass defect before you can calculate the binding energy anyway. Per nucleon for, in this case, carbon 16. Okay, so to figure out our mass defect, we're going to take the mass of the separate particles or the separate nucleons, and we're going to subtract it from the mass of the isotope, or I guess we'll say the mass of the nucleus. Okay, but when I'm saying the nucleus, I'm talking about in this case, the C16 mass. Okay, so we're going to look and say, well, what separate nucleons make up carbon 16? Well, we know that it's going to have 6 protons, and if the mass number is 16, it must have 10 neutrons. So the mass of the separate nucleons is going to be 6 times the mass of a proton plus 10 times the mass of a neutron. 0.00866. And then we're going to subtract, after we add that up, we're going to subtract the mass of the carbon 16 that they gave us. That's 16.014701. Okay. So mass defect is going to be so our mass defect is going to be 0.118879 AMU. Okay, now to figure out the nuclear binding energy, we are just going to use our conversion between AMU and mega electron volts. Every 1 AMU, 931.5 MeV. Easy, right? Okay. If we needed this value in terms of joules, we could calculate it in terms of joules. In this case, it wants to know what the binding energy is, and this is the binding energy. This is the total binding energy. But we want to find the binding energy per nucleon. Okay, there are 6 plus 10. There are 16 nucleons that make up a carbon 16. So we're going to take that value, 110.74 MeV, and we're going to divide it by 16 nucleons. And we're going to end up with 6.921 MeV per nucleon. Okay. So it really does just seem more complicated than it actually is. It's not that bad at all. So we're going to do the same process now, but we're going to do it for uranium-238. Okay. So I'm going to erase this. Same process. I really hope that that nice calendar reminder came through for you guys in the audio. All right, so going through the same process again now, but now we have many more nucleons to deal with. So the first step is going to be to calculate that mass defect. Okay, and we're going to need our, gave us a mass, yeah, they gave us a mass value. I'll write it out for the uranium-238. So the protons in uranium-238, look on the periodic table. You see that uranium's got 92 protons. So it's going to be 92 times the mass of a proton, 1.00783 AMU. Okay, and then we're going to figure out the number of neutrons by subtraction. So 238 minus 92 is going to be 146 times 1.00866 AMU. And then we're going to subtract the mass of the uranium-238 that they gave us in the problem, 238.050784 AMU. Okay, so first the mass defect, it's going to be okay, so we get a mass defect of 1.9339 AMU. So now I'm going to convert this into our mega electron volts for our binding energy. Every 1 AMU is 931.5 MeV. So we're going to get 1.801 times 10 to the 123 for our total binding energy. Okay, and then we're going to take this value and we're going to divide it by our 238 nucleons. And we get 7.569 mega electron volts per nucleon. Okay, and that's going to be our binding energy per nucleon. Okay, and that's it for the calculations for this chapter. Let us know if you have any questions.